All right, so in this video, we're kind of making sure that you've completed page one. So we want to make sure that you have completed this portion right here where it says you were going to have an activity, and I wanted you to graph it in Desmos, and you were going to identify characteristics of those graphs. So assuming you've done that first, that's the first priority, this is what we can conclude based on those observations. So um, it says, study the information collected in the table on the previous page. What general inferences can you make about the end behavior based on the degree of the function? And so just simply put, an even degree, so if it's even degree, it has end behaviors that are going in the same direction. So if it's an even degree, the end behaviors are the same. If it's an odd degree, then the function has end behaviors going in opposite directions. Okay, so that's what we can conclude. And so this is how we're going to write that notation. So we are completing the table, but we are going to identify the end behavior rules for odd and even degree polynomial functions based on the degree of the function itself and the leading coefficient. So here we have 1 and 2 are both with degrees that are even, and then we have whether or not you have a leading coefficient that's positive or negative. So I am going to fill this out so that we have the proper notation. So left end behavior, as x approaches negative infinity, when you have an even degree and a positive leading coefficient, the idea is really to start with the right end behavior first and then go back and fill out the left end behavior. So if you have a positive leading coefficient, the right end behavior is going to go towards infinity. So it says as x approaches infinity, f of x approaches infinity. And then because it's even, the left behavior is going to be the same. So then that case, we have positive infinity. Now, let's take, for instance, we have a negative leading coefficient. Again, we start on the right behavior. If it's a negative leading coefficient, the right side of the graph is going to be approaching negative infinity. And if it's even, again, the end behaviors are in the same direction. So this is also negative infinity. All right, remember with odd though, we're going to have end behaviors that are opposite. So again, with a positive leading coefficient, your right side will be positive infinity. But because it's odd, your left side is going to be the opposite. And so now let's take a look at an odd with a negative leading coefficient. We know that a leading coefficient, if it's negative, will fall to the right. And because it is odd, it is opposite. So the left side will be going towards positive infinity. So let's take a look here and complete that table. And it says that we are going to identify the zeros and their multiplicities. So let's take a look at that. You can see I've marked up the zeros. So we've got x is equal to -3. Notice that concavity changes, so that's going to be a multiplicity 3. And then we've got x equals a +1, and that is going through the x-axis, across the x-axis, without changing concavity. So the degree and type of function, well, the minimum degree that it would be is going to be a 4. Okay, so the degree is 4, and then that is going to be what we consider quartic. Okay, so that's the name of a fourth degree polynomial. And then it says determine if the leading coefficient of the equation is positive or negative, and then justify your conclusion. Then write a possible equation for the function. All right, so we always want to identify the right side first. So let's take a look at that. The right side is going down. Okay, so I can just simply say since the right end behavior is falling right, the leading coefficient is negative. All right. So we determined that the leading coefficient is negative, and we justified that by stating the fact that the right in behavior is falling to the right. And so now we're going to write a possible equation. So we're going to say f of x, and this is where we know that we have a negative leading coefficient. So I'm going to say a negative a. And then I can just put in my zeros of my function. So this is x plus 3 to the third power, and then x minus 1 with a multiplicity of 1. However, we don't need to put that little 1 there. It's implied. So let's take a look at this one. We've got a 0 at x equals negative 2. Multiplicity 1 does not change concavity. And then we've got x is equal to 1, multiplicity 2. You can see that that's tangent. This is tangent right here to the x-axis. So we've got a degree of 3. And so we're going to refer to this as a cubic function. And again, same scenario. We got to identify our leading coefficient. Well, since the graph falls to the right, since the graph falls right, the leading coefficient is negative. Okay. So our possible equation for that is again going to be negative a. This represents right here, that represents the leading coefficient. And then now we just put in our zeros. So we've got x plus 2 to the first power, it's multiplicity 1, and then x minus 1 squared, and then that's that bounce. Okay. So what we're going to do over here is, in order for you to complete the notes, I need you to do these two problems right here. And then now what we're going to do is go in and look at it from a table perspective. All right, so it says the table below shows a function values of a quintic polynomial. So that means a degree of 5. The zeros in the table are the only zeros of the function. Answer the questions that follow. Okay, so we're supposed to take a look at this and identify the left and the right end behavior of the function. So we know that this is we'll go to the right first. This is the right behavior as x approaches positive infinity. So that means we are looking at the 2 points here, and we're just looking to see what's happening there. Are we going up or are we going down? Well, we're going from a 1 to 225. So I would say that we are going up. So as x goes to infinity, f of x is also going to infinity. And then now we're going to take a look at the left side. We know that it's quintic, it's odd, it should be opposite, but let's just confirm that. So let's just take a look here. We're going from negative 10 to negative 147. So that's safe to assume that as x goes to negative infinity, y is also going to negative infinity. All right. So part B says, based on the end behavior, what must be true about the degree of the function and about the sign of the leading coefficient? Give a reason for your answer. All right. All right. So and I just talked about this just a second ago, but since the behaviors are opposites, right? So we've got a positive infinity and negative infinity in part A. Since the behaviors are opposite, the degree must be odd. Okay. The leading coefficient must be positive, right? Because the graph rises to the right. Okay, and that's because of the table values were showing that it was increasing. Part C says to identify the zeros and the multiplicities of each zero and justify your answers. Well, we already know that this is a fifth degree. So we've got to have 5 zeros. But it does say that in the table, these are the only zeros. So let's take a look at where our zeros are. Our zeros are right here. And those are the only ones. The question is, what's their multiplicity? Because it's a fifth degree. So let's start with x equals -3. All right. So we have x equals -3. And if we look, you are going from negative to positive. Okay. So we only have these two. So we know that x plus 3 is a factor. And it's got to be a multiplicity of 3 because, hold on just a second here. We know that that changes sign, and we know that this is quintic, so it's a degree of 3. So we know that we can't tell if the concavity changes just by the table. All we know is it's going from negative to positive. So we've got the -3, and we know that it crosses the x-axis because of the sign changes. Since this is a fifth degree polynomial and only 2 zeros from the table, that was given from the table, the sum of the multiplicities will add to 5. Okay, so we know that this is 3. It's either a 1 or a 3. Okay, so I can put in here a 1 or a 3. But you'll see why it's a 3 in just a moment, because we've got to add up to 5. All right, so now let's take a look at the other 0, which is, in this case, x is equal to 1. So let's take a look at what's happening here. We've got a positive and a positive, which means that there was a bouncing back. So this doesn't cross the x-axis. So at x equals 1, the graph is tangent, which indicates a multiplicity of 2. Okay. And that was because we went positive to positive on both sides. So now what we have is x minus 1 squared. Okay. So now technically x plus 3 to the third power, you could have started off by saying 1, but the problem is it says here in the table that these are the only zeros of the function. So the fact is that the zeros need to add up to 5, okay? So that's why we are saying that this has a multiplicity of 3. So x equals -3 with a multiplicity of 3, and x equals 1 with a multiplicity of 2. All right, so if you have any questions, make sure you get those addressed in class. All right, so now what I want you to do is I want you to this table on your own. I've kind of set it up for you to make sure that you can have the right notation and everything, but you'll need to have that completed on your notes. And then finally, let's take a look here. So at this bottom portion, it says, if the given function is not already factored, we need to completely factor it. We need to identify their zeros and multiplicities of the zeros, and then using the zeros and the end behavior, sketch a graph of the function. Okay, so what we're going to do is on the first one, I've already completely factored that for you. So you can look to see how I did that. We're going to identify those zeros. So if we take a look at this, this is my first 0. If it makes sense, you set each factor equal to 0 and solve. So I get x is equal to 0. I get x is equal to -2, and I also get x is equal to -2. You can see that there's a -2 with multiplicity 2. So what I'm going to do is mark those zeros up. And you don't start sketching left to right. You actually need to start sketching the right side first. Okay, so that's important. So what you do as step 1 is you plot your zeros. Okay, so that's step 1. I plotted my zeros. Then step 2 is to sketch the right side. Well, notice that my leading coefficient is negative. So I am falling to the right. Now, I forgot to indicate the multiplicities here. X equals 0 is with a multiplicity of 1. But x equals -2 is with a multiplicity of 2, which means it's going to have that kind of bounce. So now as I go through this, if x equals 0 is a multiplicity of 1, I need to be going through that graph. I need to be going through that x-axis, and I need to come back around and be tangent to that other 0. And so that's going to be what the graph would look like. Okay. Can also just verify. Remember that this is an odd degree so that the end behaviors are opposite. And that's another way for you to double check your work. All right. So let's take a look here. Let's go ahead and graph G or factor G of X. So this is 4 terms. So I'm going to go ahead and again model for you grouping. There's no GCF out of all 4 terms, so that's what I'm going to do. I'm going to focus on the grouping. So I've got x squared. I've got 2x plus 3. And then I'm going to pull out the GCF here, which looks like a -9. And then I've got 2x plus 3. So G of x is factored as x squared minus 9. And then 2x plus 3. But extra paying attention, x squared minus 9, that's a difference of squares. So that could be factored further. So you're always looking to try and factor further. So now that I've got my fully factored form, my zeros are going to be x equals 3, x equals -3, and x equals -3 over 2. Again, you just set each one of those equal to 0 and solve. And it looks like they all have a multiplicity of 1. Okay, so let's go ahead and plot those. I've got a -3, I've got a 3, and I've got a -1.5. So let's do that. And then the next thing we want to do is locate our right end behavior. So the leading coefficient is positive. So I know that I am going up. I also know that since there's a multiplicity of 1, then I've got to go through here. I've got to cut through that x-axis really quickly here. I know that that negative 27 is a y-intercept, so I'm just going to put negative 27 down here. I don't know when it curves. We'll use calculus for that, but at least at this point, we know it's got to come back up from here, and then it's got to turn around and come back here. So we need to just make sure that whatever we do, we have those components of the graph. We need